So today we're going to talk about navigation, and this will be part 1 out of 2, just because it's kind of a dense topic, so we need to cover a lot. And so we'll spread this across 2 different lessons. You'll see in front of you I put a couple charts. One of those are going to be a sectional chart, and we'll talk about that in a minute. We'll also get into coordinates today, understanding universal coordinated time or Zulu time, as well as mechanical flight computers. Starting off with sectional charts, this is going to be your primary means for navigation in aviation, and this is kind of the foundation of how we teach people how to navigate, how to fly cross country. So these charts you'll see here at the top, it has the area that it covers. In this case, it's a Los Angeles sectional chart. Below that, it'll say the scale for that chart. So sectional charts are 1 to 500,000, and that means that 1 inch is equal to 6.86 nautical miles. So these charts are designed to show topography. So it's going to show different elevations, mountain ranges, terrain. It's also going to show other things like checkpoints, which can include freeways, roads, railroads, any distinctive landmarks, and as well as airspace. You'll notice some dates at the top of this chart as well. So it's going to have an effective date, and then underneath that, it'll say 2, which is going to be the end of that range. These charts are only good for 56 days, which is kind of a short amount of time. So what that means is you always want to make sure that you have the most updated charts in hand when you're using these to navigate. They expire pretty often, so it's a good idea to subscribe to a service that ships you the newest charts. Not that they rework this map every 56 days, but they do make a few changes, and maybe something minor, like changing a single digit on a frequency, maybe changing an airport may be closed or a runway may be closed, things like that. The other chart I place in front of you is called a terminal area chart, or TAC as we call it. It's very similar to the sectional chart we just looked at, but it's half the scale. So you'll see there at the top it says 1 to 250,000. So now 1 inch is comparable to 3.4 nautical miles. So these are going to be based off of terminal areas or really busy areas like Class Bravo airspace. And they show a lot more detail because of their scale, and you can use these to navigate around those Class Bravo airspaces. The map here at the top can help you determine which cities in the country have a TAC available. So for us, we have a Los Angeles TAC. There's also San Diego, San Francisco if you go up north, and there's a couple more as you go throughout the country. So it's going to be in densely populated areas with a Class Bravo airspace. And these follow the same cycle as your sectional chart. These are updated every 56 days. It's going to be on the same cycle. So once you update your sectional, you may also want to pick up a TAC depending on the airspace that you go. Something on the TAC that's not included on your sectional charts are going to be transition routes. So if you flip it over, there's going to be these insets on the other side of this TAC here. And you can use these transition routes to transition through Class Bravo airspace. And so these identify preferred routes. They give you dimensions, and they allow you to transition through Class Bravo airspace with a clearance. And it'll have the depiction here at the top, what navigate is being used. In this case, it's going to be the LAX VOR. And then underneath that, it will have the directions. So how to use that route, what altitudes are preferred. So in this case, if you're going northbound, you're going to be at 6,500. If you're going south, 5,500. Another depiction are VFR corridors. So a VFR corridor allows you to maintain VFR through a Class Bravo airspace. It's essentially a hole or a tunnel going through the Class Bravo. You don't need a clearance for this, but there are a few rules that you need to abide by. And so just keep those in mind. You can locate flight information in a few different places, which can be kind of a frustrating part about aviation. You'll notice that not everything is located in a single place. You have to do a little bit of homework and get familiar with all the different resources and where to find information. In the case of navigation, we're primarily going to be using the legend that's on the backside of those charts. And this is what that legend would look like. It identifies and defines different symbols that you'll find on the chart. So we're going to kind of dissect this a little bit and understand those different symbols. These charts are pretty limited on how much information can be displayed. We can't tell every detail about an airport just by looking at a chart. So in that case, we need something called a chart supplement, which is this small book right here. And there's a few different sections. There's going to be 7 of these chart supplements, and they're going to cover different regions across the country. So in this case, this one's the Southwest region. So you can find any airport within these states, and this will tell you more detail than the chart would. It's going to tell you things like the runway dimensions, lighting used, tower schedule, and it's also going to have an airport diagram in the back of that and a few other things as well. Another thing I recommend people get is something called an Aeronautical Chart User's Guide. So this is going to be kind of supplemental to this legend as well. It's going to display more information than you would find on that legend, and it's also going to include more explanations. So there may be symbols you cannot find on this legend that may be a little bit more unique, is what I call them, or a little less common. And you can find those in the Aeronautical Chart User's Guide. So anything from the FAA is available as a free download. So you can download all of these as a free PDF from the FAA's website. Just Google the name along with FAA, and then you can pull those up. Doesn't have to be for the Southwest. You can pull up your specific region. If you happen to be using an electronic flight bag, it should already have these downloaded on there. So starting at the top, so if you look here at the top of that legend, it'll again have the name of that chart, followed by the area that it covers. So we're going to start there, and we're just going to go down the list right here and understand what all these symbols mean. So there's 2 lines that a lot of people overlook because it's pretty small print. And that says that airports having control towers are shown in blue, all others in magenta. So you'll notice once we start opening up these charts that runway layouts are depicted in different colors. And those colors don't necessarily match with the type of airspace it is. So for example, if an airport is shown in blue, that doesn't mean that it's a Class Bravo airport. It just means that it has a control tower. And if an airport is magenta, that doesn't mean that it's a Class Charlie airport. It's going to be a non-towered airport. So for the airspace depictions, you want to look at the lines that surround that airport, not necessarily the color of the airport itself. It says consult chart supplement for details involving airport lighting, navigational aids, and services. All times are presented as local. For additional symbol information, refer to the Chart User's Guide, which is that book I told you about. Going down the list, we have airports. So here are the distinctions with those colors I told you about. So the ones on the left are magenta, and that indicates a non-towered airport, and the ones on the right are blue, so that indicates a towered airport. Airports with an open circle are other than hard surface runways, so that means it's not paved. So it could be dirt, grass. If it has the runway layout and it's kind of an enclosed circle like this, it's a hard surface runway, meaning it's paved between 1,500 and 8,069 feet in length. If it's longer than 8,069 feet, or if they have some runways, or if they have some multiple runways less than 8,069 feet, it'll be depicted like this. So it's basically going to trace the outline of the runway itself. If there's an open dot placed at the airport, that means that they have a VOR or VOR DME at that location. If it's an open circle with an R, that means that the airport is private. So it's not available for public use, but it's still going to be depicted on these charts. So that way you know where a suitable place to land may be in case of emergencies. Also, you want to be able to find it if you do have permission and want to land there. Unpaved military airports are 2 open circles in this case. Then you got heliport, unverified, abandoned, or closed. So if you have an X on it, don't land there. If there are tick marks surrounding the airport, that means that they have fuel available. So that's one of the ways you can identify if fuel is available at an airport. And you might ask yourself, how could these tick marks be depicted on something like this? They won't. You just have to consult the chart supplement to find out. If there's a star with an open circle, it means that there's a rotating beacon in operation from sunset to sunrise. There could be other cases in which that beacon would be operating. Usually if visibility is poor, they would turn on the beacon. And like we talked about last time, all of the airspace depictions. So class Bravo would be solid blue, class Charlie, solid magenta, and then class Delta is going to be a blue dashed line like this, including the ceiling for that class Delta is going to be in brackets like that. Class Echo surface area is going to be a magenta dashed line. And then class Echo starting at 700 is going to be identified by the magenta vignette. And then it's going to be class Golf below that. The blue zipper line, like this, is going to differentiate floors of class Echo airspace. So you can see on the top side, Echo starts at 2400 MSL. On this side of it, starts at 4500 feet MSL. Some special use airspace and a couple other depictions too. So you'll see these light blue lines going across these sectional charts. And that's to indicate a federal airway, or a Victor airway is what they call them, because they're identified with a V followed by the number for that airway. And what these do is they are basically a highway in the sky. They connect VORs to one another, and you can use these as, like I said, a highway. You'll mostly use those in instrument training, but they're still going to be depicted on your VFR charts, and you're still welcome to use them. Prohibited, restricted, and warning areas are going to be these blue hash lines. Alert and MOAs are going to be red or magenta. Special airport traffic area is going to be a blue diagonal line like this. Magenta 1 is going to identify a national defense airspace. ADAs, kind of think about that as the country's border, but for airplanes. Mode Civil is going to be a solid magenta line. National security is a thicker dashed magenta line. Tersa, black line, and then military training routes. Airport data. So airports have information like control tower frequency, ATIS frequency, runway length. If a traffic pattern is non-standard, it will tell you all in this little block of information. So it's a lot of information that's condensed into a small area. And so you can see the amount of information provided in order to decipher this little block of information. So it's really good to practice, pick random airports, try to interpret what that information is saying, and then check yourself using the chart legend. So starting here, it's going to have the name of the airport at the top and the ICAO identifier. CT means control tower, followed by the control tower frequency, in this case 118.3. Then there's a star after that. What you want to look at is right here. It says star indicates operation is part-time. So you got to see the tower frequency in the chart supplement for that one. What it basically indicates is that the tower closes eventually. It's not full-time. Then there's an enclosed C right after that, and that means follows the Common Traffic Advisory Frequency, or CTAF. So putting that all together, it means control tower is 118.3, but operations part-time. Once the tower closes, that frequency will be used as the CTAF. Then we have ATIS, 123.8. So your ATIS is called Automatic Terminal Information Service. That's what you use to listen to weather at the airport. You get your altimeter setting, any notes for the airport. Underneath that, it says 285, and what that means is the elevation of the airport right here. Then there's an L, and that means that the lighting is in operation from sunset to sunrise. A lot of times you'll see that L with a little asterisk or star on the left side of it, and that means that lighting limitations exist. So you got to check the chart supplement to understand what those limitations are. Most of the time, it's going to indicate that just like the tower, the lighting goes off once the tower closes, and the pilot can control the lighting using the microphone. 72, that's the length of the longest runway in hundreds of feet. So in this case, it's 7,200 feet. then the Unicom 122.95. So a Unicom is different than a CTAF. A Unicom is what you use to communicate with ground facilities from the airplane. Most of the time, they're not going to tell you left traffic for traffic pattern, but they will tell you if it's non-standard, which would be right. So in this case, there's right pattern for runway 23 and runway 34. VFR advisories can be picked up on 125.0, and there happens to be a weather cam, and this is an airport of entry. You'll get really comfortable at your home airport. I recommend pick random airports in your area or even throughout the country. Try to decipher what this information is telling you, and it's guaranteed that you're going to be asked this on your check ride and even the written test. So the written test is going to ask you questions based off of this airport data, and you'll need to locate the airport on the figure book, then figure out what it's asking. So here's a good example. We're going to look at figure 20, and then it points you to area 2. The elevation of the Chesapeake Regional Airport is A, B, or C. So let's take a look at figure 20. Here's figure 20, and the question was sending us to area 2, which is right here. You can see the red dot with the number 2 in it, and it's asking about Chesapeake. So there's Chesapeake, and you can see the airport data right here underneath that airport, and it's asking what the elevation is for this airport. So we got Chesapeake, AWAS 3123.675, and then down here there's a number 19, L55123.075. Then it says RP 23. So out of those, which one do you think is the elevation? This one's referring to the pattern, so it says right pattern for runway 23. Can't be that one. So your options are going to be either 19 or 55. So the 55 is going to be the length of the longest runway at that airport, so it's going to be 5,500 feet, and that leaves us with 19, which is the elevation. So our only choice is C, 19 feet. Moving down, we get into communication boxes. So communication boxes are going to point you to information on how to communicate with a flight service station. A lot of times these will be co-located with a nav aid, like a VOR. So it'll have the information box or communication box. If it's bolded, it means that a flight service station is connected to that nav aid. And then a few frequencies will be available how to communicate with flight service. So flight service, again, provides weather information as well as flight planning. So if you need to amend a flight plan or if you want to get en route weather, you can contact flight service and get some assistance. You could see some cross-hatching right here, and that means that the frequency is being shut down. And then at the top, there's a couple other frequencies, and you would use those to communicate with flight service. If there's an A, it means that ASOS or AWAS is available. Sometimes you'll see that frequency followed by an R, which means receive only. And that means that the flight service station receives your communications on that frequency. So it's from their perspective, not from the perspective of the pilot. Underneath, you'll often see the flight service communication. So this one's Miami radio. Underneath that, we have radio aids or nav aids. So depending on the type, there could be a few different depictions. If it's just a standalone VOR, it's going to be this hexagon shape right here, the dot in the middle. If it also has distance measuring equipment or DME, it'll be enclosed in a square. Standalone DME will just be a square. If it's a VOR with a TACAN, stands for Tactical Air Navigation, then it's going to look like this. NDBs would look like this, and if they have NDB and DME, it would look like that. So again, we're going to talk about VORs in part 2 of our navigation lesson. So we've mentioned it a few times, it might be a little bit confusing, but these are just ground-based facilities we use to navigate, and they could be standalone, which is what we just looked at here, or they could be located at an airport, in which you would have an open dot at that airport. Here's another practice question, and it's sending us to figure 24. Area 5. So the navigation facility at Sulphur Springs is a blank. So we want to look at that area and identify what type of navigation facility it is. So let's take a look at figure 24 right there. And it's pointing us to Area 5, Sulphur Springs, SLR, right here. So we want to know what navigation facility is this. So that's showing us a hexagon, but it's also surrounded by a square. So we have a VOR, and the square indicates DME, which is distance measuring equipment. So DME can tell you your distance from the VOR if you have the correct equipment on board your aircraft. So looking at our answer choices, we have A, VOR DME, which is what we just looked at, or it could be ADF or VOR. So we're going to go with A. So really quick, I just wanted to show you a quick tip that not many people know about. If we look at the testing supplement on page 13, I believe. There it is. Page 13 or legend 1. It actually gives you the legend for the sectional chart. So based off the question we just looked at, that could actually help you a lot. So you could look at the radio aid, VOR DME right there, and look up the symbol that we need to answer that question. Aside from that, something that also could help you a lot would be airport data. So if you need to look for airport elevation or understand a particular frequency, you can reference this table to jog your memory a little bit, and it's a little bit easier than having to memorize everything. Next, we'll look at obstructions. So these obstructions could be standalone, or they could be group obstructions, and they could be unlit or they could be lit. So if these obstructions are 1,000 feet or higher above the ground, it's going to have this Eiffel Tower looking shape like this. If it's above 200 feet but below 1,000, then it's going to just be this triangle shape or pyramid shape like that. If there's high intensity lighting, it's going to have these lightning bolts coming off of it like that. If it happens to be a wind turbine, then it would look like this, just looks like a windmill. Group obstructions will just have multiple peaks to it. It doesn't identify exactly how many there are, but there is a group obstruction that exists. If there's a wind turbine farm, like you would see out towards Palm Springs or Las Vegas, then it would look like this, and it would surround the general area that covers. Below the wind turbines right here, we have a few different numbers, and those are telling us the height or the elevation of these obstructions, so that way you can avoid them. The top number indicates the height of the obstruction above mean sea level, or the elevation above mean sea level, MSL. Below that is the height above ground. An easy way to think about it is if I take my water bottle right here, and we'll just say that this water bottle is 1 foot and this table is 3 feet high. So if I place my water bottle on top of this table, that top number right here is going to be 4 feet. Because if the ground is mean sea level to the top of the water bottle, that means it's 4 feet. Now the bottom number would only be 1 foot, because it's taking out the elevation of the ground and just measuring the height of the obstruction, not necessarily the elevation included with the terrain. Another example, referring to figure 23, area 3, what is the height of the lighted obstacle approximately 6 nautical miles southwest of Savannah International? There we have figure 23. Here's area 3, and if you look below that, it says Savannah. And kind of a hard part about this is it's nearly impossible to see the airport information for Savannah. And it's a little bit camouflaged. We see right here it says Savannah Hilton Head International. So the question is asking, what's the height of the group obstruction 6 nautical miles to the southwest of Savannah? So these are always oriented north. So north would be this way, east, south, and west. So we're looking towards the southwest, 6 nautical miles. We know that this first line right here is 5 nautical miles from the airport center. So 6 should be right here. And we know that's a group obstruction because there's multiple peaks. So these are the numbers associated with that group obstruction. There's another one right here and another one right here. But we're going to be looking at this one. So at the top it says 1548 and below that it says 1534. So in my opinion, this question is worded poorly because it says the height of the obstruction rather than the elevation. But this question is asking for the elevation of the obstruction. So if you remember, the top number will be the elevation and the bottom number is just the height of the obstruction above ground. So this means this tower is 1534 feet tall, including the elevation of the terrain is going to be 1548. So that's what the question is asking. What is the height of the obstruction? And it's 1548. So look at our answer choices, and it should be A. Another symbol you'll see is called maximum elevation figure, and that's depicted as a large blue number like this on your aeronautical charts. And what that number shows you is the highest elevation within a quadrant. So that could be man-made or it could be natural. So it could be towers, trees, whatever, within a specific quadrant. So a quadrant, we haven't talked about it yet. A quadrant is made up of these lines of longitude and latitude like this. So it makes a little rectangle, and that's referred to as a quadrant. Within each quadrant is you'll see a large blue number like this, and that's referring to the maximum elevation figure. So there's a few things that go into that, but it's rounded up to the nearest 100 value. And so in this case, it'd be 13,500. Now this doesn't mean that you need to stay above that altitude within that quadrant. It's just to warn you that there's an obstacle within that quadrant, and you need to remain at least 13,500 feet in order to clear it. So it's more of a warning, and so you could use that especially at night or if visibility is poor or if you happen to be lost. But you don't necessarily need to plan around that number. Just be aware that that elevation will exist within that quadrant. Some miscellaneous ones, you'll see a bunch of these depending on where you fly. It could be aerobatic practice area, glider operations, hang gliders, parachute jumping. So if you fly near an area that has a lot of skydiving, then you would see this parachute jumping. Stadium, space launch area, isogonic lines, which we'll get into. A really important one would be these VFR checkpoints. It'll be a magenta flag. It'll have the name of that checkpoint or waypoint, followed by the visual point code that you could put into a GPS in order to identify it using GPS. Typically, these will be identified using landmarks, but it could also be an airport. So if you notice that an airport has a red flag and the name of that airport is underlined, that means that it's co-located with a VFR checkpoint. Getting into latitude and longitude, I usually like to tell people we don't typically use latitude and longitude or coordinates on a daily basis in modern aviation, but it will definitely come up for your written test, so it's important to understand it. So lines of latitude are the lines that run horizontally and parallel to the equator. So those go east to west, and that's what's depicted on this image right here on the left. So lines of latitude increase as you travel north from the equator, and they decrease as you get closer to the equator. And lines of longitude run vertically, and those run parallel to the prime meridian. So as you go west of the prime meridian, those numbers increase. As you go closer to it, they decrease. So understanding those lines a little bit more, we always read coordinates as latitude first and then longitude, and these are read in degrees. So because you're training in the US, all these examples are going to be in the Western Hemisphere and the Northern Hemisphere. So it becomes pretty predictable how you can count these numbers in order to figure out where an airport is located. So the way these numbers work, you may have seen them written somewhere before, but we always read latitude first and then longitude. So in this case, it'd be 48 degrees north, 105 degrees west. Each degree is further broken down into 60 minutes. So think about a degree as an hour. And each hour is broken down into 60 minutes. You could break it down even further. 60 minutes gets broken down into 60 seconds, but we typically can't see that much detail on a chart. So most of the time we'll just use degrees and minutes. So in the example right here, there's 105 degrees west, and then as you travel to the left or further west, the number increases to 106. That total distance is 60 minutes. Each of these individual tick marks is 1 minute, and each degree is broken in half on your charts. So you'll see a line right here that doesn't have a number on it, and that's just the midpoint between 105 and 106. So this would actually be 105 degrees, 30 minutes is what this line is. There's larger tick marks as well. You can count those as 10. So it goes 10 minutes, 20 minutes, 30 minutes, which is what we looked at, 40, 50, 60. Once you get to 60, it's the next degree. So the pattern that you want to understand is as you travel to the left on these charts or west, this number increases. As you travel north, the number increases as well. The reason why I bring that up is because sometimes on these examples on your written test, you may be given a figure that looks like this, and the only numbers provided look like that. And so you need to understand that as you go up, that number increases, and as you go to the left, the number increases. So you have to do a little bit of counting in order to find these airports. In the example in the figure right here, it's locating Poplar Airport. It already tells you 48 degrees 7 minutes north, but let's look at that to understand why. This horizontal line is our first line of latitude, and that's 48 degrees, and we know that it goes up. So 48 degrees, 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7. So that's how they got that number. Now the line of longitude is 105. So as we go to the left, it increases as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 105 degrees, 11 minutes west, and then we can locate that airport. So let's put that into practice and look at figure 20, area 3. The question's asking, determine the approximate latitude and longitude of Currituck County Airport. All right, so this one's a nice challenging question. It's fairly easy to find the first line of latitude, right there at 37, and a lot of people struggle to find the line of longitude. And the reason for that is because it's right here. Kind of difficult because it's kind of congested right here with a lot of different information. But you'll notice those are the only numbers we're provided on this entire figure. So you need to remember which direction to count as we find Currituck. So there's the airport, and those are the numbers. So our first step is find latitude. So if this line is 37, here's our next line of latitude, but you'll notice that there's no number associated with that number, or there's no number associated with that line of latitude. If you scroll to the bottom, you can see the top of what it should have been if this figure wasn't cut off. So what that represents is as you go down, it goes 37, off the chart is actually 36, and this is the midpoint between those two. So this should be 36 and 30 minutes. So if this is 30, then we go 29, 28, 27, 26, 25, 24. So horizontally on the line of latitude, this is located at 36 degrees, 24 minutes. Now the longitude, once you can find it, it's a little bit easier. So here's 76, and it's just to the left of that 76 right here. As you go to the left, it counts up. So it's one tick mark over, so it's 70 degrees and 1 minute. If you look at our answer choices, it should be A. We'll do another example, and I find this style to be a little bit easier, so you'll probably find this a little bit quicker. So in this case, we're going to look at figure 21, area 3, and we're trying to find out which airport is located at 47 degrees, 21 minutes, 30 seconds north, 101 degrees, 1 minute, 30 seconds west. Here's figure 21, and we're looking towards area, actually we're not given an area because we're just given the coordinates. So first we want to find out Which airport is located at 47 degrees 21 minutes and 101 degrees 1 minute? Luckily, these ones are a little easier to identify in this one. Here's 48 degrees, but we're trying to find 47.21. So here's 48. Scroll down. This should be 47.30 right here. 30, 29, 28, 27, 26, 25, 24, 23, 22, 21. So the airport should be along this line. Using the answer choices, you can kind of figure it out, but we'll keep going. So here's 47.21. Again, you can't really see seconds. It gives you 21 minutes, 30 seconds. It's impossible to look at that much detail at this. Then the next step is 101 degrees and 1 minute. So here's 101 degrees and 1 minute over. There's one tick mark, and we'll be at Washburn. There you go, Washburn. Next, we get into Coordinated Universal Time, UTC. We also call it Zulu. So you may have seen some times with a Z afterwards, and that means Zulu. In aviation, we use a 24-hour clock. You could think about that as military time for anyone that's used military time before. And the way that a 24-hour clock system works is that instead of reaching 12 o'clock noon and then starting over at 1 o'clock, 2 o'clock, 3 o'clock, it continues to count upwards until you get to 24. So let's say 12 o'clock noon, and then 1 p.m., instead of 1 p.m., it would be 1300. 2 p.m. would be 1400, kind of like it says here. 6 p.m. would be 1800, 11 p.m. would be 23. So instead of going to 24, it just goes to 0. So if 11 p.m. is 2300 hours and you reach midnight, the clock starts at 0. And then once you reach 1 a.m., it's 100 hours. 2 a.m. would be 200 hours. So the AM times are a little bit easier to figure out. Where you get a little bit more confusing is in the afternoon or the PM. So any weather reports and your flight plans are going to be based off of Zulu. So you need to understand how to convert local time to a 24-hour clock, as well as make the adjustment to Zulu, which is an additional step from there. Luckily, on the written test, you're going to be given a figure that looks like this, which includes the conversion table along with it. So depending on your time zone or the time zone in the test question, it gives you the conversions on the table. So you don't need to memorize this information. So from the US to Zulu time, we're adding time because it's going to be ahead of our clock, and it's based off of Greenwich, England. So if I'm based in the Pacific time zone, right now it's daylight savings because it's summertime. We are adding 7 hours. If it's standard time, we add 8 hours. And then you can see if you go to the East Coast, you're going to add 4 hours for daylight savings and then 5 hours for standard time. So let's take a look at an example. This one says, refer to figure 27. An aircraft departs an airport in the Eastern Daylight Time Zone at 9:45 for a 2-hour flight to an airport located in the Central Daylight Time Zone. And the question says the landing should be at what coordinated universal time? Before we jump into this, just want to clarify a couple things. People tend to overthink it a little bit. You don't need to do the conversion between the time zones. If you just take the time plus the flight time and convert that to Zulu, you don't need to worry about time zones because you're just jumping to Zulu, which is a universal time. You don't really need to worry about the time zones. So in this case, we're leaving at 9:45 for a 2-hour flight. So that puts us at 11:45. And we're departing the Eastern Daylight Time Zone. So if we just look at figure 27, Eastern Daylight Time Zone. So here's figure 27, and we're leaving the Eastern Daylight Time Zone, and it tells you to add 4 hours. So in order to go from local time, which is Eastern Daylight Time, to Zulu, we're going to add 4 hours plus your 2-hour flight. So you're taking your departure time and adding 6 hours because that's including the conversion plus the 2-hour flight time. So 9:45 plus 9:45 plus 6, and can anyone guess which one that would be? So easy way to do it, 9 right here, 9 plus 6, that gives us what, 15? So then we got 1545 Zulu. You'd still get to the same answer if you went between the time zones. It's just an extra step you really don't need to do. If you just take your departure time, add the 2-hour flight, and then convert it to Zulu, it saves you an extra step. Another example right here, referring to the same figure, an aircraft departs an airport in the Central Standard Time Zone at 9:30 CST for a 2-hour flight to an airport located in a Mountain Standard Time Zone. The landing should be at what time? So a common trap that people fall into with this one is they convert it to Zulu when the question doesn't ask you about that. It just wants to know what the local time should be. So in this case, you do want to use the time zones, just not Zulu. So if we depart at 9:30 and it's a 2-hour flight again, that puts us at 11:30, but then again, we're going from Central to Mountain Standard Time Zone. So Central Time to Mountain Time, we're going to go back an hour. So if we look here, typically we would add 7 to get to Zulu. For Central Standard, we would add 6. So we're decreasing 1 hour as we go west in the US. So the question, 9:30 plus 2 hours puts us at 11:30, but then we're going to the west, so we're subtracting 1 hour, and that would put us at 10:30. We'll get into a little bit more about actual flight planning or plotting. When it comes to measuring direction, we use a plotter that looks like this. So hopefully everybody has one. And this is what we're going to use with your sectional charts to not only measure distance, but determine your true heading by using those plot points right there. So we use these to determine our course, and this is kind of step 1 of the flight planning process. And we could also measure the distance between points, which will give us performance information, like how long it's going to take us for this flight, how much fuel we're going to burn. After we determine our true heading, there's a few other corrections we need to make. One of those is going to be magnetic variation. So there's a difference between true north and magnetic north. If you look at this picture on the top left here, the red dot is representing magnetic north and the yellow dot is representing true north or geographic north. So where we consider the North Pole to be is actually different than where your magnetic compass is being attracted to. So because those points are different, you can see right here there's some lines of longitude. They go straight towards true north. And these red lines are going to be the magnetic lines of force right here. So because your compass is going to be pointing you towards these red lines, but we're navigating based off of these sectional charts using true direction, we need to convert between those two different numbers. So that's going to be called magnetic variation, or the difference between those two. On your aeronautical charts, you'll notice a magenta dashed line with a number on it, and that's called the isogonic line. That number is showing you the difference at that location between magnetic north and true north. So you'll notice, at least in the western half of the US, these lines will say east on it, which is kind of confusing because we're in the western hemisphere, but the reason for that is because these red lines are pointing towards the east of true north. So we need to make that correction in order to, for our flight planning to work correctly. So whatever this line says, if it's east or west, you need to incorporate that in your flight planning. If it's an easterly variation, you're going to subtract it. If it's west, you add it. Way to remember that is east is least, west is best. So least implies subtraction, best implies addition. And something else to keep in mind is magnetic deviation, which is going to be the error in your magnetic compass in the aircraft. And that error is going to be caused by materials or different electrical fields in your aircraft. Some basic calculations that you want to be able to do. We're going to talk about flight computers in a little bit, but just using a basic calculator, some simple math, you want to be able to do these things kind of freehand as well. If you're trying to calculate time, you take your distance being flown, divide that by your ground speed. If you want to calculate how long you've traveled or the distance you've traveled, take your ground speed, multiply it by time. Determining your ground speed, take your distance, divide that by how long it took you to travel that distance. Speed conversions, if you want miles per hour, you take your current knots, multiply that by 1.15. And lastly, fuel consumption. Take the time, multiply it by gallons per hour. That works for if you're traveling a long distance and across multiple hours. For us, since we're in a small aircraft, even our cross countries are fairly short compared to larger planes. Most of our legs are going to be measured in minutes instead of hours. So you could take those minutes, divide that by 60 to get a fraction of an hour, and then multiply that by gallons per hour for your aircraft. As an example, let's look at this at the bottom. So how long will this flight take and how much fuel is going to be burned? So GS means ground speed. So considering our ground speed is 95 knots and the determined fuel burn is 8.4 gallons per hour. And the distance is going to be 130 nautical miles. So with that one, we're going to start by dividing our distance by our ground speed, because that's what we're doing right here, is getting our time first. So that comes out to 1.37 hours. Our next step is fuel consumption. So we're going to take that time and multiply it by gallons per hour. And that gives us 11.5 gallons. So if we're going this fast and traveling 130 nautical miles, we're going to burn 11.5 gallons of fuel. So putting that into practice a little bit with our plotter is, let's look at this figure right here. So figure 20, determine the magnetic course from First Flight Airport, Area 5 to Hampton Roads Airport, Area 2. This one's a little bit challenging. So here's First Flight at the bottom right corner. And then Hampton Roads is right here. So your first step is to overlay your plotter and then determine the heading, or the true heading, between those 2 points. So the question is more specific though. It's asking the magnetic course. So what you want to do is determine your true heading, find the nearest isogonic line, and then account for that magnetic variation, and that will give you the answer. You also want to make sure you have the direction correct on here. So we're going from First Flight to Hampton Roads. So we're traveling this direction. We're traveling to the northwest. So one of the things you can do with these types of questions is determine the approximate heading just by looking at it. Since these are oriented north, we're traveling northwest. So we already know that that heading is going to be somewhere between 300 and 360 degrees. Looking at our answer choices, there's two that are close. We already know that B should be incorrect because that's implying a southeast heading. So our answer choice is either A or C. So what you want to do is get your plotter between those 2 points, and then you should come up with a heading of 321 degrees. Most of the time people will come to that answer and they'll pick C, but since the question is asking for magnetic, you want to find the nearest isogonic line, which is right here, 11 degrees west. So west is best. 321 plus 11 gives us to answer A, 332. Next, we'll get into flight computers, which in a sense is basically doing all those calculations that we just looked at and using a tool to help us get there instead of just having to use a calculator. Typically, we teach people how to use a mechanical flight computer. You're more than welcome to use an electronic one throughout flight training. You can bring it on the written test with you and even the checkride. But typically, it's best to use a mechanical one at first to understand the concepts, and then you can use electronic if you'd like. So with this flight computer, there's two sides to it. The front side right here is the computer side. We use that to calculate a few different things. And if you flip it over, the back side is called the wind side. So we use this to calculate wind correction as well as ground speed. Using the computer side, you'll notice that this, if you play with it a little bit, this inner dial rotates. So that inner dial typically is going to tell you things like time. The outer scale is going to tell you a few different things depending what you're trying to calculate. Could be fuel burn, could be distance. We'll start out with something fairly basic. We'll do conversions. So we're going to convert between miles per hour and knots. And to demonstrate that, because it's a little bit difficult to walk around and show everybody, is I like to pull up a little simulator. So you can do this at home too if you don't have one yet. Is University of North Dakota has developed a simulator, and at this point it's accessible publicly. May not be that way forever, but for now it's kind of nice to use that at home. So you can rotate this inner dial, and what we're trying to do is convert between miles per hour and knots. So if you look to the left side of your flight computer right here, there's a small bracket. It says knot and stat. That stands for nautical miles, and this stands for statute miles. So for our question, we're trying to convert between 100 miles per hour to knots. So these numbers on the inner scale right here, you can change the decimal place to represent whatever you want it to. So in this case, we're going to look for 100. You'll quickly notice that there is no 100 on the scale, but we could take 10, shift the decimal place over to the right one, and that represents 100. So if I take that 10 and align it right there, statute miles, 100, and then we get nautical miles underneath this arrow right here. So whatever number is opposite to this arrow is how many knots per hour you're traveling. So here's 80, 85, 86, 87 is the nearest one. So in this case, 100 miles per hour is equivalent to 87 knots per hour, or nautical miles per hour. So there's the answer right there, 87. Now looking at time, speed, and distance, we already touched on that a bit with some of the computation methods for doing that. But using a flight computer, a little bit daunting at first, but you'll figure it out pretty quick. The question is, how much time will it take to fly 120 nautical miles at a ground speed of 100 knots? So luckily, you can cheat. I don't condone cheating, but luckily these flight computers have directions on them. If you look at the face of your flight computer, it'll tell you right here what to do. So set miles per hour under the index, which is this black triangle right here. So you just move the inner dial until you align your speed with this triangle. So for us, we're traveling 100 nautical miles at a ground speed of 100 knots. So what we want to do is align this triangle with 100 knots. There's the index, and this is going to represent 100 knots for us. So under the directions, we did the first step. We know the distance, we're trying to understand the time. So distance is going to be measured on this outer light gray area, and the time is going to be told into this inner circle right here, or the inner scale. So if we're going 120 nautical miles, there's 12, shift the decimal, we're going to pretend that's 120. Opposite to that, here's 70 minutes, 71 minutes, 72 minutes. So here's 70. If you go further in from there, it says 110. That's just 1 hour, 10 minutes, which is what 70 minutes is. So it's going to take us 1 hour and 12 minutes to travel that distance. There you go, 72 minutes, 1 hour, 12 minutes if we're going 100 knots. So here's a problem looking at fuel consumption, and just quickly looking at an example right here. How much fuel will be used during a flight of 2 hours and 30 minutes if the fuel consumption rate is 8.2 gallons per hour? So we're flying for 2.5 hours, and we should be burning 8.2 gallons per hour. I mean, you can quickly figure that out just using this method up here, but for practice, we're going to look at the flight computer. So I'll set it back just so we can look at the directions a little bit. set your gallons per hour under the index, and that will tell you your total gallons over time. So we already know the time, so we're going to look opposite to that to look at how much fuel we're going to actually burn. So our first step is to align the index with our gallons per hour, and in this example is 8.2. So take this triangle. 80 is going to represent 8.0, 8.1, and there's 8.2. So that represents how many gallons per hour we're burning. And we know that we're going to be going 2.5 hours. So now we're going to look, I'll zoom in just so you can see a little bit better. So you may need to tilt your head a little bit, but here's 2.5 hours, which is equivalent to 150 minutes. And our fuel burn is going to be on the opposite side of that. So here's 20 gallons, 21. Each of these lines represent 2. So this is 20.2, 20.4. So this is 20.5. So it's going to be 20.5 gallons. And there's our answer right there. All right, save the best for last. So everybody's least favorite is airspeed calculations, as well as figuring out density altitude. This one might take a little bit of repetition, so take your time, practice a few examples. If you need extra help, I can walk around and help you guys out with this one, but it's asking what is the true airspeed and density altitude if the indicated airspeed is 130 knots, OAT, which is outside air temperature, is negative 15 degrees Celsius, and the pressure altitude is 5,000 feet. So I'm just going to write that down really quick as I switch screens here so I don't have to refer back to it. So 130 knots, outside air temperature is minus 15 degrees Celsius, and pressure altitude is 5,000 feet. Zoom back out. So for this one, the directions are right here because we're trying to do an airspeed correction. And the directions say set pressure altitude opposite temperature in the window. And the window that's referring to is right here. So you'll see a couple windows at the top of your scale. This top one is representing density altitude. This one is to calibrate or align your pressure altitude with temperature. And this is a higher altitude scale over here. So to start off, try to make it simple, is this is your pressure altitude window that's white here at the bottom, and this is your temperature on the top. So to start off, I'm just going to line the zeros, make it a nice baseline so that way it's a little bit easier to see. So what we want to do is align the pressure altitude with the temperature provided. So pressure altitude was 5,000 feet, and the temperature was negative 15 degrees Celsius. So this 5 is 5,000 feet. So I'm just going to move the scale to put 0 right here. It's a little bit counterintuitive because your temperature is positive to the left. You'll see right there, plus 50, and it's negative to the right. Our example was negative 15, so what you want to do is rotate this to align negative 15 with 5. So here's 0, negative 5, negative 10, negative 15. Pressure altitude is 5,000 feet, temperature negative 15 degrees Celsius, and now we got those two aligned. Our next step is to look up at your density altitude. Here's 0, 1,000 feet density altitude, 2,000, about 2.5. So your density altitude is 2,500 feet, which makes sense because your pressure altitude was 5,000 feet. The temperature was really cold, which increases air density, meaning the airplane is going to perform like it was at 2,500 feet, which is good for performance. So our next step, fortunately you're not done yet, we need to convert the airspeed, or we need to correct the airspeed. So our airspeed was 130 knots in the example. So for this, it says opposite calibrated airspeed on the inner scale, read true airspeed on the outer scale. So this 13 is going to represent our indicated airspeed. So there's 130. Look opposite to that, and that will give you your true airspeed, which is the speed that you're actually traveling through the air. So here's 130, 131, 32, 33, 34, 135. So between 134 and 135 is our true airspeed due to that air density. So in the example, we just rounded up to 135 for the answer. Now, if you flip over that flight computer, we'll look at the wind side. And again, if you look to the very top, you have directions right there for you. So if you ever get stumped or lost on a question or how to do these steps, just take a step back, look at the instructions, and you should be able to figure it out pretty quickly. So we use this scale for a couple things. One is wind correction. So depending on the wind during your flight, you may need to alter your heading a little bit in order to keep on the desired flight track or flight path. And another thing this will do is it gives you your ground speed. So wind is going to affect your ground speed, or how fast you're actually traveling over the ground. So if you have a headwind, that's going to negatively affect your ground speed, meaning you're going to go slower, and it's going to take you longer to fly from A to B. If you have a tailwind, that's going to increase your ground speed. You're going to get to your destination faster, which is good for cruise. So first example we'll look at, we're considering the wind is 150 at 20 knots and our course is 95. So I'm just going to write this down again so I don't have to go back. So I can take the same scale. I'm just going to flip over to the wind side here. Zoom out. First thing you want to do is you'll notice there's a small circle in the middle of this wind scale. What you want to do is slide the sleeve, because you can slide this up and down on your flight computer, is set this grommet, which is what this circle is called, set that grommet to 100. So 100 is going to represent our baseline, or 0. And so you want to set up the scale first. Zoom in a little bit for you. And then if you look at the top, step number 1, set the wind direction under true index. So we already know the wind direction from our example. It said 150. So you rotate this dial until you get 150 under this white triangle, or true index. So there's 170, 160, and 150. So that's the direction the wind is coming from. Your next step, mark wind velocity up from the center point. So it actually does mean mark. So you could use a pencil or a pen and make a small dot on this, and it's pretty easy to erase. You'd use your finger, eraser, it comes off pretty easy. So what we want to do is from the center point is count up until we get to our wind velocity. So the wind was 20, there's 20 right there, and we're going to make a mark. So you can do that with your pen or pencil. Step number 3, set the true course under the true index. So now we're going to rotate this and put our course at the top. So our course was 95, right there. So east is 90, there's 100, so 95 is right there in the middle. So you'll see how that dot that you made shifted to the right. So if you were to imagine that the nose of the airplane is upward and the tail's down here, the wind is coming at you from the front, but also to the right. So you know it's a quartering headwind. So a headwind is going to slow you down. So in the end, you know your ground speed is going to be slower than your starting speed. And since it's coming from the right, you're going to have to point the nose of the airplane slightly to the right to compensate for that right crosswind. So what that eventually does to your course is going to increase in degrees. Since our starting course was 95, it's going to increase, because if you look to the scale right here, if I point my nose to the right, this number goes up. If that crosswind were over here, that number would go down if I pointed to the left. All right, next step, slide the wind velocity mark to true airspeed. So next step is you're going to move that sleeve until that red dot lands on your true airspeed, which is the airspeed that was indicated in the example. So right now it's on the 110 line right there. So there's 100 and there's 98 right there. Step number 5, ground speed will read under the center. So wherever your grommet landed, that's going to be your ground speed. So we can see right here there's 80, 81, 2, 3, 4, 5. So about 85 knots. So we started off going at 98 knots, but since we had a headwind, it's going to slow you down to now your ground speed is 85. The very last step, wind correction angle reads between the center line and the wind velocity mark. So our wind velocity was the red dot right here, and that's just about on the 10-degree mark right here. So we're going to count to the right 10 degrees. It says right here, wind correction angle to the right plus. If it was to the left, subtract. So if it was 10 to the right, we're going to add 10 degrees to our original heading, which is 95. So we come out with 105 for our new heading. And we ended up with 85 for our ground speed. So here's the answer right here, magnetic course, 95, right here. 85 knots for ground speed, and magnetic heading is 105. All right, next question we'll look at says, if a true heading of 135 results in a ground track of 130, and a true airspeed of 135 knots results in a ground speed of 140 knots, the wind would be from. So what we're going to do for this one is we're going to move the sleeve until that center grommet lands on our ground speed. So there's 140, which was the ground speed given in the example. And then you're going to rotate the dial to put our track under the true index, which is 130 right there. Our next step is to find our true airspeed. So here's 140, and our starting airspeed, or true airspeed, was 135, which is right here. And since the wind causes us to deviate to the left from our starting point, we're going to count to the right 5 degrees along our true airspeed. So here's 135. There's 5 degrees to the right, so we're going to drop a mark right there. And our next step is we're going to rotate this until that line is centered. So there's our dot, and we're going to keep rotating this until it's centered, right about there. So at the top is going to represent the direction of the wind. So there's 240, 245, about 246. And we're going to count up from our starting grommet right here. And there's 140, 150, there's 10, 1, 2, 3. So that means the wind is coming from 246 degrees and the velocity is 13 knots. Looking at our answer choices, looks like it will be C. Just another mention of electronic flight computers. You are allowed to use them. Depending on the flight school you attend, they may only prefer mechanical, they may prefer electronic. My recommendation is understand the steps using a mechanical one, and then if it's in your budget, you can go out and get an electronic flight computer. Sporty's makes one. There's also a CX3, which they tend to be a little expensive, but if you prefer, you're more than welcome to use it. You're allowed to bring this into your checkride, your practical test, as well as your written test. You're allowed to bring this, as long as it's not, programmable, you can't save information in it. The written test also has an electronic flight computer within its software. From what I understand, it's not the best, and so you may prefer to bring your own that you're comfortable using. So whatever you prefer, practice with that. Whatever practice questions you use, continue to practice using the method that you plan on bringing to the written test and the checkride. There's a couple methods we use for navigation. First one is pilotage, and the second is dead reckoning. And these rely on a couple basic principles. We basically create a course, fly that course, and then make position corrections and checks along the way. Pilotage refers to navigating using landmarks. So you have to see objects or landmarks in order to fly towards them, and we use those as checkpoints essentially. So you could use a lake, you could use a freeway intersection, you could use a prominent landmark wherever you happen to fly. Next step is dead reckoning. So we use that based off of calculations, which is basically what we've practiced so far. We're using aeronautical charts, measuring courses, making corrections. So in themselves, each one of these have pros and cons to them, but together they tend to be very accurate. So we tend to use dead reckoning on our flight planning, and then we combine that with pilotage as we fly using prominent landmarks. Here's an overview of all the steps involved in flight planning. We take our true course, which we use with our plotter and sectional. Then we make wind corrections. That gives us our true heading, plus or minus magnetic variation. That gives us a magnetic heading. Then we apply magnetic deviation, which is provided by the compass deviation card in your aircraft. And the last step is your compass heading. So once you make all these corrections, you should be able to accurately fly using your magnetic compass in your airplane. This is just an overview of terms we've covered. So if you want to understand them a little bit deeper, take a look at this. When it comes to determining checkpoints, a good rule of thumb is place checkpoints about 15 to 20 nautical miles apart, and that will guarantee that you stay on track. So if you pick points that are 50, 100 miles apart, it's really easy to get off track. So the closer your points are to one another, it's easier to stay on track and make sure that your course is accurate. Also pick points that are, I call them prominent, so easy to see from the airplane. You don't necessarily need to overfly these points. You should be able to see them outside of your window. Some course considerations: consider the feasibility of the flight. So whether your aircraft can actually perform that flight. So if your aircraft is required to gain 10,000 feet within a couple miles, probably not very feasible. You also want to consider airspace, whether that's special use airspace like prohibited, restricted, as well as any surrounding airspace, especially if it's busy. And then when it comes to flying the course, your objective is to stay on track. So what you want to do is monitor your ground track, monitor your calculations, and then make corrections as you go. We're going to finish up with kind of a difficult question for some people, but we'll look at figure 20, and it says, en route to First Flight Airport, Area 5, your flight passes over Hampton Roads Airport at 14:56, then Chesapeake at 15:01. What time should you arrive at first flight? First thing you want to consider at the bottom right here is that sectional chart figures are not to scale. So instead of using your plotter, what you want to do is use the scale that's associated with the figure to measure the distance between these points. So here is the figure. And if we zoom in a little bit, we could find Hampton Roads right there and Chesapeake. So your first step is to measure the distance between those points. So using the scale from the top of your figure, you could use your scratch paper, create your own scale based off of this figure because it will be accurate. Measure the distance between those 2 points and you'll arrive at 10 nautical miles. So then what we want to do is measure between Chesapeake, which was right here, and first flight. Using the scale at the top of the figure, you'll see that we get 50 nautical miles between those two airports. And if we put it all together, in the example, it took us 5 minutes to go from Hamptons to Chesapeake. So that measured distance was 10 nautical miles. We did that in 5 minutes, which comes out to 120 knots. So now we know our ground speed, and we can apply that to the next distance. So from Chesapeake to first flight came out to 50 nautical miles. Using our ground speed of 120, you divide the two, you come up with 0.42 hours, which is a fraction of an hour, which is equivalent to 25 minutes. So it's going to take us 25 minutes to go from Chesapeake to first flight. If we add that to our time of 15:01, we get the answer of 15:26. So I'll go ahead and hand out today's quiz and let me know if you have any questions.